Hello, everybody. This is a special presentation on the joy and mysteries of topology, mostly three-dimensional. So three-dimensional topology is an area of mathematics in which I spend a lot of time doing research in. And I want to share some of my research experience as well as some famous results in topology, especially two and three-dimensional topology. I also will talk about what mathematics is all about, what topology is all about, and what does it look like to do research in mathematics. So let's get started. The joy and mysteries of topology. Okay, I hope you can see the slides, the joy and mysteries of topology. And I say mostly, oops, I am going ahead, so let's go backwards. And here we go. So I say mostly three-dimensional because I will be talking about the other dimensions as well. All right, so let's get started. Before I get into topology, though, I wanted to ask you what mathematics is. What is mathematics anyway? I know this is a philosophical question, and there are people who actually studied the philosophy of mathematics. In fact, they even have annual conferences. And I have attended a few of those, and it's interesting. They ask questions like, what numbers are, what is mathematics, and so on. Whatever you think mathematics is, or most people just call it math, I think it should be called mathematics. But whatever it is not just about numbers and arithmetic. And I hate to say, but this is what most people, especially in the United States, think about when they are asked what math is all about. Okay, so it's about numbers, adding and subtracting and so on. No, it's not. And when somebody is not very good at adding numbers, that person say, well, I'm not good at math. And but trust me, there are plenty of mathematicians, like high caliber mathematicians, who are not very good at numbers and arithmetic. Okay, maybe I'll share a story about this later. It's not just about even procedures and formulas. Okay, so you apply formulas to come up with correct answers. That's really not much. There's no mathematical activity in that procedure. Sometimes maybe there is, but not very much. And certainly it's not about getting your homework right and getting good grades in your math course. Okay, that type of activity is really not mathematical in the correct sense of the word. It's really about these abstract entities. And here's the key, right? Abstract, okay? We mathematicians look at abstract things, try to find connections between them in terms of relations and functions, right? So somebody said, maybe correctly, mathematics is the study of functions and relations, which are of course based on sets. And then you talk about like numbers, right? Because mathematics does deal with and involves a lot of numbers. But what is a number? Okay, does a number represent quantity? Point on the number line? Well, I mean, that's sort of circular reasoning, right? Because you can't define number as a point on the number line, because what is a number line? Well, it's a set of all the numbers. And it's not, because you can talk about, like 3 apples and 5 apples. So the natural numbers may make sense. You don't talk about -3 apples, but there is a way in which we can correctly understand negative numbers. How about numbers like pi and e and these irrational numbers, transcendental numbers? Yeah, there is a point on the number line representing e and pi and so on. So in that sense, you can call them numbers, and maybe that's true. Well, how about numbers like I or 2 minus I, complex numbers? They certainly don't represent a point on the number line, because those are not real numbers, right? So you can even spend hours discussing what we mean by a number, right? So it becomes deep, all right? And then we can talk about other structures. And in fact, this is really the core of the mathematical structure, things like sets, and pretty much in these days, everything in mathematics is defined in terms of sets. A set with certain properties, we can call them groups or spaces. And we try to find common properties among these mathematical entities. So that's what mathematics really is. And mathematical activities involve these things: discovering, proving, and just analyzing these properties among and within these abstract structures. So this may sound silly. What mathematics is that's what mathematicians do. It sounds silly, but in some groups of people who study philosophy of mathematics, some people think that this may be the best description of mathematics, what mathematicians do. I personally don't like this because, mathematicians brush their teeth and they eat their food, and those are not a part of mathematics. Okay, and let's go to what mathematicians do then. And I want you to know that the most and the biggest, maybe the most, the important part of the activities of a mathematician is to prove theorems, okay? You may start with a conjecture, or one may start with a conjecture, because as a person studies various objects and patterns and behaviors, they start to see certain rules, certain patterns. And then they may, come up with a guess, intelligent guess, and those are called conjectures. And then you have to either prove it or disprove it. How do you disprove something? Because, like, let's say you want to prove that, something is true under these circumstances. And if you want to prove it false, disprove it, then you need to have a counterexample. And sometimes a great discovery of a counterexample could be a tremendous gain in the world of mathematics. So some counterexamples are so famous that they have their own names. Okay, so and also a mathematician may come up with interesting questions. By asking good questions, you too can advance mathematics and contribute to the future of mathematical research. So these are the things that mathematicians do, not just doing and carrying on calculations. Calculations probably aren't the main part of mathematics, right? Also, you can prove something in ugly way or in elegant way, okay? And in fact, Paul Erdős, the famous mathematician in the 20th century, who died about 10, 20 years ago, the Hungarian gentleman, he was talking about the book. And when he talked about the book, it is this book that's somewhere in the heavenly places that contains all of the elegant proofs of mathematics. And he knew many of them. He came up with some of those himself. And he was certain that there is the book, okay, that book somewhere out of this world that would contain every elegant proof in mathematics. And yeah, we look forward to seeing that someday. All right, so one of the things that mathematicians do, and now we're going into the area of topology, is to classify things, okay? Can you classify a collection of objects that have certain properties? All right, and for instance, here's a good example. About 100, maybe 150 years ago, some mathematicians started to look at knots. Okay, what are knots? Well, you take a string and you tie the both ends of a string, but in doing so, you can make a knot, and then you can connect them back. So this is really called an embedding of a simple closed curve in a three-dimensional space. That's the definition of a knot. A continuous embedding, of course. And so these are some of the pictures that early knot theorists have come up with, okay? And this is really the first 15 knots from the simplest one called the unknot, or sometimes called knot, like N-O-T space K, N-O-T. And then there's another one here, which is called a trefoil. This is called a figure 8 knot, and so on. And these are pretty much completely classified up to a certain level. Okay, but this itself is not a very trivial task. Okay, and for instance, you see here in this picture, you have 3 points of intersection, self-intersection, right? You see the points are sort of knotted, okay, or you can see the intersection when you have the picture like this. Yes, 1, 2, 3, right? Well, it turns out that if a knot can be drawn on a piece of paper with only 3 intersection points, it has to be the trefoil knot, okay? All the other ones, except the unknot, would have to have at least 4 here's one for one. This knot is called the figure 8 knot, and it is called 4, 1. And this is the only one that has the crossing number of 4, which means that you have to have at least 4 crossings in order to draw this on a piece of paper, and so on. Okay, and so and this was a tremendous amount of work when you go up to like even 10 crossing numbers. Anyway, so that's an example of a classification. You know, how do you classify knots, for instance? Today, I want to talk about classifying manifolds. Okay, what are topological manifolds? First, let me explain what topology is. Some people confuse this with another discipline called topography, which has to do with maps and geology. Okay, so you know, if I say I'm a topologist and I study topology, some people think, oh yeah, you work on maps, you know, like elevations and so. No, 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 I don't do that. Okay, sometimes topology is called rubber or rubber sheet geometry. Okay, so it is geometry with flexible length, okay, shapes and angles. All right, so the angles really don't matter. Okay, in other words, we consider this to be the same as this, which is the same as this and same as this. Okay, in fact, these are all just finite length, segments, right? A topologist is a mathematician who cannot distinguish a coffee cup from a donut. It's a famous statement. And you can see the deformation of a coffee cup into a donut right here. See, you start with this. Notice here, this part is just one big chunk, right? So you can sort of make it shallow and smaller, like over here. And then you can make that part sort of go away. And then you still have a hole. Now, this hole is, of course, that little tiny hole at the handle of the cup. And then you can keep deforming this in a continuous fashion. And continuity means that you don't, rip it, you don't break it, you don't cut it, you don't make a hole. And so you can see that the coffee cup is really the same thing as a donut. Okay, these two spaces, although they look very different, are called topologically equivalent, or more precisely, homeomorphic spaces. So two spaces are homeomorphic. That means topologically the same. Okay, so for instance, here is the letter A, right? Well, that's the same as this. Okay, and I can just go ahead and do something like this. These are all the same. And if you notice here, you have two ends, and then you have two vertices of where three edges merge, right? And you can see that these pretty much are the same objects, all right? And so you can classify all of the capital letters of the English alphabet according to their topological equivalence and so on. Okay, a topology is actually a topology. When we talk about a topology, it's actually a collection of sets. And an element of a topology is called an open set. So you may have heard, I'm sure you have heard of open set on the real number line, an open set on the plane, and so on. And that is a topological term, an openness. Okay? And the set is open if it is in the topology, and the set is closed if its complement is open. And the set can be both open and closed, and many sets are neither open nor closed. So, and we have certain axioms and conditions to define what a topology is. Okay, and then within topology, you can study geometric topology or algebraic topology or set theoretical topology, and there are many sub-branches of this discipline. Okay, so what are we trying to classify? Okay, we are trying to classify the set of objects called topological manifolds. All right, what is a manifold? An n-dimensional manifold, okay, sometimes called an n-manifold, is a geometric object that locally, and this is the key word, locally looks like the Euclidean n-dimensional space. Oh yeah, so what is an n-dimensional space? R1, okay, this is the one-dimensional Euclidean space, and this is just a line, okay, so this is just a infinitely long line, and if you are standing at this point, all you see is the right hand and the left hand side, and you cannot go in any other directions, right? R2 is when you have the cross product or the Cartesian product of the two, and so you have, R2 is the two-dimensional space, otherwise known as the plane, the Cartesian plane. R3 has 3 dimensions, right? So now these are the familiar spaces that you know about, okay? But what objects would have a local structure of R2, for instance? What looks like a plane? Okay, and I will talk about this in more detail in a moment. But a manifold can have a boundary. It does not have it doesn't have to have a boundary. It can be bounded. It doesn't have to be bounded. Okay. What do you mean by a boundary? Well, if you have a piece of paper locally, it does look like, if you pick a point, it does look like a point on the plane, right? But it has these edges. And so if you go to the end, you can't go anymore in that direction. So, and these sides are called boundaries. Okay. Now, if you have an open, let's say this is going to include all the endpoints. If you have a square that does not include its endpoints, okay, then you don't have any of these points. Okay. In other words, every point you're standing here in this open, square is going to locally look exactly like R2. All right. So this is called a two-dimensional manifold without boundary. The first one is a two-dimensional manifold with a boundary. You can even talk about this entire plane. Okay. Now that is unbounded because it just keeps on going forever. Okay. So you can have a bounded manifold, unbounded manifold, and a bounded with a boundary or bounded without boundary, and so on. If a manifold is what we call compact, and I'm not going to go into all the details. This is one of the key words in topology, compact. Okay, and you can think of this as closed and bounded, but the compact manifolds without boundaries, those are the ones that I will be talking about. These are called closed manifolds. Okay, so let me go on. There are a lot more I can say about these things, but that's not the aim of this talk. So, okay, so let's go to let's start with a where we should start, okay, which is the one-dimensional space. Okay, so what are these one-dimensional manifolds, or called one manifolds? Okay, so it's something that locally looks like a line. All right, and number one, you have this line itself. Okay, so this, suppose you have an infinitely long line in both directions. That certainly is a one-dimensional manifold because every point on this line looks like a point on the line, of course, right? A circle is another one because locally, if you're standing here, all you see is this side and this side. Now, remember, you forget the fact that you see a curvature here because you actually live outside of this world of the circle. And so you can see it's curving here, but if you're standing right here, you don't see that, okay? And so a circle locally looks like the line. Every point, okay, looks like an interior point of this line. So it is a one-dimensional manifold. And in fact, this is the only one that is compact because it doesn't go forever. I mean, it does go forever, but it comes back to the same point. This is different from a line, an infinitely long line. These are not topologically equivalent, okay, but they are both one-dimensional manifolds. How about any open interval? Let's say you have an open interval from 0 to 1, okay, not including the two endpoints. Well, that still locally looks like a manifold, right? So if you're at any point, remember, there is no endpoint. So if you're at any point, you can go to the right or go to the left, just like you're over here or over here. So an open interval is a one-dimensional manifold. If you have a closed interval, let's say from 0 to 1, now we have a little problem. Two little problems, okay, the two endpoints. Because if you're standing here, you are no longer, well, your world no longer looks like a point on the plane where you can look at the right or the left. Okay, if you're standing here or standing here, you only see one direction. The other direction has no world, okay? So this is slightly different. In fact, it's very different. And we can call it a one-dimensional manifold with a boundary. It's still, obviously it's bounded, but it also has the boundary, which consists of 2 points, okay? So this is a one-dimensional manifold, but this has a boundary. This does not have a boundary. You say, well, how about 0 and 1? Aren't they boundary points? Well, no, because 0 and 1 are not in the universe of this open set, right? So the open set is like this line. They are topologically equivalent. How about a ray? Okay, well, again, you see this one point here where at this point, that point is different from these interior points. And so a ray is not a equivalent to a circle or to a line. It is, I mean, it is a one-dimensional manifold with a one boundary point. Okay, so what I mean by, I should mention before we go too much further, when I say a circle, I mean not just what you think is a circle. Okay, and in fact, any simple closed curve would be called a circle in the world of topology. So circle itself is that, and of course, an ellipse is okay. And in fact, squares and rectangles and triangles, these are all circles. Why? Because these are all topologically equivalent. All right. In other words, what you can do is you can round this up, continuously. So you can start bending and bending and bending and then bending. You can make them longer or shorter. Of course, the length doesn't matter. All of these are topologically equivalent to a circle, simple closed curve. And so, and by the way to go from here to here, just like from a coffee cup to a donut, is called a deformation, or you can call them a homotopy. And so you can talk about defining a homeomorphism between this triangle and this circle, and that's a continuous deformation from here to here. If there is such a map, which is called a homeomorphism, then we call those two manifolds or the objects topologically equivalent. Now, if you're at the COC library going upstairs, not taking the elevator, but going from the ground floor to the second floor, you see this nice piece of art on the wall. That's a pretty big piece. You probably saw that, okay? And I thought, man, how nice that they have a beautiful illustration of this deformation or homotopy. You start with a circle, okay, and then right after that, in a continuous fashion, it starts to go make it, round and round and round, and eventually you end up in this outside circle. So a deformation from here to here will show you that the square is homeomorphic or topologically equivalent to a circle. All right. So anything like that. In fact, if you just to try to be funny, and if you have this, okay, that is also topologically equivalent to a circle. All right. Now, if you cut this right here, then of course it ceases to be a circle, right? Or if you go like this, okay, that's not a topologically equivalent to a circle. All right. So just so you know what I mean by that, let's now go add another dimension. We go to two manifolds, two-dimensional manifolds. So what locally, so what should I say? What manifolds are such that every single point locally looks like a point on the plane, okay? So you can think maybe in this way: if you lived in some ancient world and in the middle of the desert, and all you see is a flat, land around you, what do you think the world or the earth looks like? Okay, so you're standing here, and locally, all you see is this is a plane, okay, and you don't see anything else as far as you can see. Well, you could be living on a plane, and let's say you keep walking and walking and walking, and you don't see any end. Okay, you can just keep walking forever for as fast as you can, and you don't go to any edge. Okay, so you may actually be living in the entire plane. It could be bent, it could be flat, we don't know, right? But that's a possibility. If, however, if you start walking here, okay, or if you start sailing, like Columbus did, and then somehow you can't come back to the same port in the world, how in the world could it be possible, right? If you live in a flat plane, like some people thought the earth was flat. Well, if you continue to go straight and comes back, there's got to be something different about this universe than the flat plane, right? And so that sort of, they thought it proved that the world is a sphere. Did it? Is that a proof that the world is a sphere? If you have something that locally looks like a two-dimensional space, and you just keep going and it comes back from behind you, all right? Well, it could be, but it's not a proof of it, right? In fact, the world the Earth could have been like a donut. And if you keep going here and start sailing here, you come back to the same, point. If you start go this way, you come back to the same point. So, just the fact that you started to go in one direction and comes back to the same point does not mean that you live on the sphere like this one. Right? So definitely a sphere is a three-dimensional manifold, two-dimensional manifold, right? If you are right at this point, you can't see this, but if you pick any point here on this, right? Let's say right here. As far as you can tell, if you are standing right here, all you see is just local, thing that looks like a plane. And so this is a two-dimensional manifold because locally it looks like a point on the plane. Same thing here, right? If you are standing right here, all you see is plane around it. So this is a two-dimensional manifold. And if you are thinking of two-dimensional manifolds without boundary, okay, you have the sphere and you have the donut. Is that it? Well, what happens if you have two donuts together? Okay, well, how about three? How about four? How about 15, right? So you have infinitely many of these. All of them are compact manifolds, closed manifolds, in the sense that their volumes are bound, or the surface area is bound. It doesn't go forever in space, and it has no boundary, right? So any other two-dimensional manifolds can you think of that has no boundary? Okay, there are some. Okay, so let me give you some interesting pictures here. Right now, you may be familiar with some of these things. First, you have the sphere. Okay, so the genus. Oh yeah. So the way you classify, and by the way, the two-dimensional manifolds have been completely classified for many years. So we do have a complete answer to a two-dimensional manifold classification problem. So you have the sphere, and the way we classify these the two-dimensional manifolds is by Euler, the number called the Euler characteristic defined for each manifold. That's called the Euler number. Right? And it turns out the sphere or anything that is topologically equivalent to sphere, just like a whatever, okay, a rock or something, the surface of the rock it has the Euler characteristic too. All right, and the genus is also related to the Euler characteristic, and that's 0. So either the Euler number or the genus would define what that two-dimensional manifold is. Okay, and so the sphere is 1, and in geometry, in the sense of geometry, it is called a positively curved space. And I don't have time to go into it, but the positive curvature is one that characterizes the sphere. And then you have the torus. Now, this is the torus, okay? And the torus is basically, and the way you make this torus, think of this flat surface, okay? So this is, maybe you can think of a square, part of the piece of paper. All right. And the way you construct this torus is this: you identify all the points on the edge, on the top edge with the bottom edge. Okay. So if you do that, you get a cylinder, right? And then you connect or you glue the points on this edge with that edge. So now you connect this and this together, and then of course you have this torus. Okay. So it really does have a flat geometry. And the Euler characteristic of the torus is 0. Genus is the number of holes. It has a one hole here, so the genus is 1. And this is the only one that what we call admits a flat geometry, or the 0 curvature. All right. And then we can talk about the two of these put together. So this is a double torus. Okay. The Euler characteristic keeps going up by 2, down by 2. So the sphere has the Euler number 2, or the characteristic 2. Torus has the number 0. The double torus has number -2. And the genus is, of course, 2 because it has 2 holes. And you can keep going, right? And so you can have a bunch of these interesting, you can just keep adding holes, okay? And so you can keep decreasing the Euler numbers by 2 every time you make a hole, and the genus increases by 1. Okay, and in a sense, those are the only ones. And that is, if you think of the orientable ones. All right, there are some weird situations where you, for instance, all right, if you, and you probably know this, but if you take a long strip of paper, and if you glue this side and this side together, okay, then of course you just have a cylinder, a long cylinder like this. But if you twist it, then you get a picture like this, right? And this is the famous, what do you call that? Does anybody know what this is called? It is called the Mobius band, all right, and or Mebius or Mobius, right? And so this is the strip that has no inside or outside, right? So if you keep following here, going in here, and then you start to go outside, and then go around, and then comes back inside. So this is a strip without the traditional two sides, inside and outside, are merged together. You can do the same thing with this one. All right. So you notice here, I have this cylinder, which I created over here. And if instead of gluing these two circles together to make the torus, you make a little twist, right? So if this is, let me try to make it a little bigger, right? If you have this, right, and if you glue this with a different orientation like this, you have to make a twist. And you say, well, I can't imagine that. And you're right, you can't, because this doesn't embed into three-dimensional space. So you have to use your imagination. The result will be this, okay? So this is called the Klein bottle. It is the theoretical construction by Klein, and you can see this bottle has no inside and outside. If you pour things in here, okay, like you put milk in here, great, and then somehow it just comes outside, and it is strange. This is the sort of non-bounded, or the this is like the Mobius band, except this has no boundary. Okay, so this is the compact and closed manifold, two-dimensional manifold. Each part, each point still locally looks like a two-dimensional plane. And so this is a non-orientable example of a two-dimensional manifolds, right? The Euler characteristic of, oh yeah, and there's one more, the projective plane. I really can't explain that for you. It's basically half of the sphere. You take the top half of the sphere, and you have this half and this half, and then you identify these points with these other points, you close it up, and then you have this non-orientable plane called the projective plane that has the Euler number 1. And if you put two of them together, you have this Klein bottle. Okay, the Klein bottle, just like the torus, has the Euler characteristic 0. They are both Euler characteristic 0, but this one is orientable, this one is non-orientable. And those are it, okay? And so you can actually prove, and somebody did prove this many, many years ago, that these are the only ones, only two-dimensional manifolds, okay? And this one, of course, has the boundary circle. And by the way, the boundary is only one circle, not like two. Like, if you have a cylinder, like a pipe, you have two circles as boundary. This only has one boundary, one component in the boundary. But if you're talking about the two-dimensional manifolds without boundary, then you are talking about torus or these handle bodies. Those are the only orientable ones, and the non-orientable ones are one of these plus the the Klein bottle. And there is a way to just put them together. You just make a tiny hole here, and just glue them together, and you get something non-orientable. All right, so the complete classification of two-dimensional manifolds has been done. All right. Okay, so now we go to, let's add one more, three-dimensional manifolds. What manifolds, or what topological objects locally look like a three-dimensional space that we are used to? Okay, so we live in a world, we live in a three-manifold, the universe, right? And do we know what the shape of our universe is like? Like, if here's the Earth, and if you keep going forever, is it possible for us to be able to come back from the other side? Maybe. Okay, we haven't tried yet, because our space, or the world, the universe, is so big that nobody has gone far enough to be able to go back. Maybe you can't do that. Maybe we can. There is some evidence that maybe this kind of thing is possible. People have been studying physics and cosmology, and they study these light coming from different directions, and there is a possibility that we live in a closed up, compact universe. Maybe someday we'll find out. Maybe someday we can't. Okay, is our universe curved? We don't know that yet. Okay, but anyway, in order to classify these three-dimensional manifolds, this turns out to be a much more difficult problem than these surfaces, the two-dimensional manifolds. It took them years, in fact, over 100 years to figure this out. Is it solved? Yes, it is solved, but very, very recently. Okay, so geometry played a major role in this, and it didn't, I mean, the geometry played some role in two-dimensional manifolds, but in three-dimensional manifolds, this was a crucial step. What makes it even more complicated is that if you go to, if you are in dimension 3, the first thing you have to do is you have some strange manifolds that are locally look like, they all locally look like our three-dimensional space. And the first thing you have to do is to decompose them along the torus or tori. Tori is the plural of torus. And after a canonical way of decomposing this, each piece is supposed to look like one of the 8 geometric objects. Okay, that's the whole idea. Well, there was a conjecture, and the conjecture was after a certain decomposition, every closed 3 manifold can be classified into 8 geometric categories. All right, and so there was a fine paper written by my advisor when I was in graduate school and so on. But let me just give you an example of a 3-dimensional manifold. Now, there is a thing called a 3-dimensional sphere. What is a 3-dimensional sphere? It is not what you think it is. Okay, you're thinking of a ball. Okay, that is certainly 3-dimensional if you include everything inside. But see, that is just the 3-dimensional ball because you have the boundary, which is the surface, right? Okay, so let me go back and see if I can make sense out of this. If you have 2 copies of um, two-dimensional disks. All right, so these are basically circles. You can even cut 2 pieces of paper into 2 circles, right? And just try to identify, glue together these boundary points. Okay, and of course interior points aren't identified, right? So what do you get? Well, you get the top half. The first copy 1 becomes the top half, and copy 2 becomes the bottom half. And you notice here, if you glue these 2 pieces of cloth or paper along its boundary, you can sort of imagine this becomes a 2-dimensional sphere, right? This is called the S2. This is what we normally call the sphere. Topologically, you can extend it, you can make it bigger, you can make it round, and so that's how you built the 2-dimensional sphere, even though this lives in a 3-dimensional space. Okay. Now, in the same way, think of the 3-dimensional ball. Okay, so this is like a ball with every point in interior point included. Take 2 of these. Okay, and then, and again, this is where it sort of blows your mind. Glue each point of this boundary surface together. Okay, so it's like so if you're in the middle of this, if you start walking away to the North Pole, as soon as you get to this point, then you will be coming back from this. And so just like here, if you start going this way, you'll start coming back here. In the same way, you glue these 2 solid balls together to make a compact universe, and that is the 3-dimensional sphere. Okay, and that 3-dimensional sphere has a positive curvature, and it is one of these geometric categories, one of the 8 geometric categories. Okay, so the classification theorem, or the classification problem for 3-dimensional manifolds, took a lot of twists and turns, no puns intended there. But the positive curvature version, which is a spherical version of this, was this was a conjecture by this man named Henri Poincaré. Okay, and Poincaré was this French mathematician that says everything that is homotopically equivalent to the sphere has to be the 3-dimensional sphere. 3-dimensional sphere is written as S3. That's the one I was just talking about. Okay, there is no boundary. Every point does look like the point in the XYZ, space, and so on. But interestingly enough, and again, I don't have time to talk about the difference between the homology and the homotopy, but there are three-dimensional objects, three-dimensional manifolds that are not spheres, but homologically speaking, they are the sphere. These are called fake sphere. These are not spheres, but they have certain properties that are like the sphere. And those are called fake homology spheres. But with homotopy, they couldn't find any. Now, here's, and again, you don't have to understand this to appreciate the question I'm going to ask you. All right, let's say you are trying to find a object with certain property, okay, like this fake homotopy sphere, and you can't find it. And in fact, you spend years and years and years trying to find a certain object called the fake sphere, and you can't find it. But you can't prove that such a thing does not exist. So then what do? You wait until somebody else comes. What happens if that person can't find it? Okay, so this is the dilemma of a mathematical research project. If you can't prove it, and if you can't come up with a single counterexample, what do? And the best you can do is to continue working on it, either to prove it or to find a counter example. And that's what took mankind over 100 years to come up with. All right, the classification of three-dimensional manifolds really took off, and and I will tell you how this ended. Okay, after over 100 years since Poincaré came up with this conjecture, we have two main characters. There are many more characters. Many of them are still contemporary mathematicians, but the man named William P. Thurston, or Bill Thurston, came up with his conjecture, which has to do with the negative curvature case. All right, so let me go back again. Remember, we are talking about these 8 geometric categories. One of them is the sphere, and the Poincaré conjecture was the one that says if something is positively curved like the sphere, basically it must be a sphere. That's really not the precise statement, but that was his conjecture. He couldn't prove it. He died, like everybody does, and the problem was unknown. Okay, and even back in the 1990s, when I was a graduate student, the problem was unknown. So imagine a bunch of people trying to solve this problem here, and people thought this will take much, much longer. Okay, the positive curvature aspect of this geometrization or the classification problem. The negative curvature side, it's called the hyperbolic geometry side, was the conjecture was made by a man named Bill Thurston back in 1982. He actually proved this is true for certain manifolds, especially the thing called the Hawken manifolds. All right, and he actually won a big prize for this. The Clay Institute awards young mathematicians this thing called the Fields Medal, which is equivalent to the Nobel Prize, except Nobel Prize has no mathematics award. So we have the Fields Medal, which is like the highest award in the world of mathematics. Thurston, won this award for basically really this question, to ask this question, if a three manifold satisfies a certain property, is that hyperbolic? That was the question. And then 20 or more years passed. Many people still try to prove this, and the other conjecture. So Thurston's conjecture for the negatively curved spaces, and the Poincaré conjecture for the positively curved three-dimensional spaces. And the century came and went, and a new century, the 21st century came, and out of nowhere, basically, a Princeton researcher named Gregory Perelman, okay, a young mathematician, thereto unknown to most people, came up with a very strange theorem, and a very strange way to prove something really big. This is back in 2013. And what he did is actually prove something much bigger than this, that included both of this negative curvature side and the positive curvature side. So in one shot, to the dismay of many topologists, using language which is very foreign to even to the expert topologists, using geometric objects like the flow and so on, he actually proved both the negative and the positive curvature versions of this classification theorem. And now this problem of classifying three-dimensional manifolds is considered to be complete. There is an additional story to this, and this is a very strange thing. Remember, I told you this. Oh, yeah. By the way, Bill Thurston was somebody I knew personally, and so when I was so he was a professor at UC Berkeley, but at the same time, there is a if you're familiar with Berkeley, you can look at the top of the hill from the campus of UC Berkeley. And I never was a student officially at UC Berkeley, but I was a visiting grad student there for 1 year. If you look at the hill, if you look up at the hill, there's a science museum, and then there are two buildings. One is a space research building, and then the other is a smaller, much more humble building, and that is the Mathematical Sciences Research Institute, MSRI. Thurston was the director of that place back in the 1990s. And I would talk to him, and he was very kind to me, not very kind to many other people. Maybe I shouldn't say that. Anyway, he passed away. I would say about a few years ago, but he won the Fields Medal for proving a part of this hyperbolization or geometrization conjecture, which is his own conjecture, right? Perelman's work probably was much more significant in the sense that this proved the rest of his conjecture and Poincaré conjecture. But as soon as he was offered this Fields Medal by the Clay Institute, he actually said, you know what, I don't want this. Now, by the way, this came with $1 million award. Who would turn down $1 million? For some reason, for him to become famous and to be a recipient of such a great award was not a part of his life. So he refused. He went home to Russia, and nobody knows where he is. Well, I should take it back. He probably knows where he is. His mom probably knows where he is. But the rumor is that he went back to live with his mother in some small village in Russia where he's from, and he is living happily, peacefully and happily ever after, without that $1 million reward or the fame. Places like BBC and other agencies have been looking for him, but he is nowhere to be found. All we know is that he is living somewhere, according to some friends that who may or may not know exactly where Perelman is. But he stopped doing all mathematical research, and he is not um, somebody that we can locate anymore. All right, so looking back, I just want to close this with some personal experience, or maybe a story or a few stories. All right, so I did my graduate work in Virginia Tech, and then I went to Ann Arbor, University of Michigan, and then I spent a year at this MSRI, the Mathematical Sciences Research Institute up on the hills of Berkeley. When I finished my degree, I had the privilege of working with some of the best three-dimensional topologists in the world at the University of Melbourne in Australia. And then I did some work in Tokyo Institute of Technology. And we were all working together to do a little part of Thurston's conjecture. Okay, and this was only like 20 years ago. And of course, now it's all obsolete, thanks to Perelman, who used a very unconventional method to prove both the negative and positive sides of the classification theorem. But what's interesting is, you can do all the research. And by the way, when this problem was solved, it didn't make it into a headline news. People probably just went, and this went unnoticed because mathematical research is not uh, a cool thing everybody in the world talks about, right? I mean, if there is a breakthrough in physics or medicine, or even like in biology or something, I think that becomes a big topic. But not so in mathematics. There are two sides of mathematics. One is pure mathematics, and the other is applied mathematics. You probably know this by now, right? Pure mathematics is the one that I have been talking about. Topology is a very pure side of mathematics. I don't know if you recognize these people. This man, the famous British professor of mathematics, G.H. Hardy. Okay. Um, and then this other man is this person who never got a formal education from India, but he was invited by Hardy to do collaboration. And this guy was incredible, Ramanujan. And there is historical context in what I'm about to say, but Hardy is known as, with a quote, I have never done anything useful. Imagine that. And he spent an entire life doing mathematical research, some great mathematical research. And he said, I have never done anything useful, quote unquote useful. No discovery of mine has made or is likely to make directly or indirectly, for good or ill, the least difference to the amenity of this world. And the context is, many people are going to war. Mathematics and science were used to develop, bombs and weapons, sometimes weapons of mass destruction. And he did not want his research to contribute to these purposes. And so to him, the activity of mathematical pursuit was just a pure thing. And you do it not for the money, just like, Perelman thought, and it's not for fame, it's not for prestige. You do it because you are interested in it. It's like the mountain climbers who are saying, what do you climb mountains? Because, I mean, what do you climb a mountain? Because it's there. Why do you solve a problem? Because it's there. And then you go on once a problem is solved. All right. Unfortunately, or maybe fortunately, this man, both of these men were very good number theorists, and some of their incredible results in number theory are now helping us do e-commerce and everything on the internet, because the encryption, cryptology, cryptography, the online security, in a very, very real sense, are based on the study of prime numbers. Okay, and you may have heard of the coding and decoding using prime numbers. Their mathematical research is making it possible for us to carry on our e-commerce on the internet. So too bad that this is not true, but I think at this point he probably doesn't mind anymore, because he is no longer alive. Okay, so there are some suggestions here. I mean, this is just an extra piece of information, but if you are interested in, maybe a study of pure mathematics, or people who actually studied pure mathematics, or even fictions about pure mathematics, you have these movies and books that you can read, or watch, or read. Right? Imitation Game, many of you probably have seen this. It's a story about Alan Turing, who was a pure mathematician, but he also, because of that interest in pure mathematics, he helped develop computers. And in fact, this may be the reason um, when of the end of the World War II. And so you can look at that, and it's a fascinating story about how war was won by this by a mathematician in England. Right? And the man who knew infinity is about this man, the Ramanujan, that I was talking about. This man right here. Okay, and that's also a very cool book. And I mean, it's a movie, but there's a book by the same title, The Man Who Knew Infinity. A Beautiful Mind. This is an Academy Award winner. I think it's a Best Picture in the year it was released, and it's about the American mathematician, John Nash. And and of course, some of them exaggerated in the movie, but it's a great movie about a man who had some mental difficulty. Um, so hallucination in the book, I think his disorder was more auditory. He would hear things that really didn't exist. But anyways, that's a great story based on a true story. And then you have a few other ones, mostly fiction. Hidden Figures is not a fiction. It's based on a true story about these three African-American engineers slash mathematicians that worked for NASA. And so on. Stand and Deliver is a story about an AP calculus teacher right here in the Los Angeles County. All right, in terms of books, there's, imagine this. There's one book written about one number, if you can call this a number. It's about I, and the name of the book is An Imaginary Tale: The Story of I. And these are all books written for general audience. You don't have to be a mathematical researcher to understand or appreciate this. There's another number written about one number, another book written about one number, and the title is E. That's it, lowercase e. The subtitle: The Story of a Number. Um, some of you probably know this is my favorite number. I believe this number E holds the universe together, and it is the most important real number by far. And there's a whole book written about this one number. if you're interested in aesthetics and philosophy, how music and logic and mathematics and art work together, there's a book called Gödel, Escher, and Bach, An Eternal Golden Braid. Right? An old book, fiction, Flatland, is mathematical irony and metaphor, um, sarcastic, maybe, novel about the British society of about 100 years ago. This is an old book. There are like two sequels to this, Flatterland and Sphereland. All of them are great books, I think. And then there are some other modern ones. You can find all of these in Amazon, I am sure. Math Art, The Golden Ratio, The Beautiful Numbers in Nature, Beauty of Numbers in Nature, A Passion of Mathematics, Mathematics Devotional, and The Man Who Loved Only One Number, Only Numbers. This is a story about the man named Paul Erdős, who was a famous number theorist. Okay, so this pretty much concludes what I was going to say. I told you at the very beginning, I was going to tell you a story about how, mathematicians may or may not be very good at arithmetic. All right, so back in, I would say about 1999, there was a international conference. I was living in Tokyo at that time, and there was an international conference called Geometry of Non-Positive Curvature. Sounds really exciting, right? So I flew to Nashville from Tokyo, and it was I think, at Vanderbilt University or someplace. And there, I met some of the most renowned mathematicians of the day. There are people from Europe, Israel, Africa, Asia, just all over the place, South America, North America. And some of the people, that I just admired because I know these are very famous people. And a group of about 7 of us went out to lunch to a sandwich place in downtown. And so we were all eating at one table. And of course, some of the menu items were more expensive than others. A couple of them had alcoholic drinks. So at the end of the lunch, we were trying to figure out how much each person is supposed to pay, because the bill was just one bill and we didn't want to ask them to split the bill. And back in those days, everybody paid by cash, I think. So we were looking and we couldn't figure out exactly, how to split the bill. And so we were just struggling and struggling. And then the waiter of the sandwich place in in Tennessee came to our table and said, "Oh, that's okay, guys. I was never good at math either." And we looked at each other. Remember, these are some of the most famous mathematicians of the day. And so we looked at each other and we smiled at her and we left enough money and we just left the restaurant. And so that tells you, okay, that mathematicians may not be good at arithmetic. And in fact, it's sort of typical. Many people joke and say, well, I don't do arithmetic in public. Right? But what they're incredible is that abstract thinking, maybe the spatial mind, what the eyes and the mind to see similarities and differences, relationships between 2 or 3 objects that are mathematically abstract and mathematically elegant. And that's what mathematicians do. And so this is where we enjoy, this is why we enjoy pure mathematics, to see things, whether these results are useful or not. And that's irrelevant to pure mathematicians. There's a problem, it's interesting, let's solve it. And so classification problems in 2 and 3-dimensional manifolds were 2 of the examples that illustrate that fact. And by the way, anything that's higher than 3, like 4, 5 dimensions, those turned out to be actually not too hard. They are, in a sense, relatively easy compared to 3. The dimension 3 turns out to be the hardest problem. And now, in 2003, the problem was solved. So, and topology, I believe, is in good shape. All right, I hope you learned something. And if you have any other questions, you can let me know. And I hope you will pursue some of these ideas maybe in the future. Well, thank you for watching, and I hope you will continue to, pursue these wonderful things that you find only in the world of mathematics, which is abstract, and maybe eventually you'll find that book that Paul Erdős was talking about. All right, take care. See you later.